This is the screencast for section 8.4, example 5. We're going to evaluate the integral on negative infinity to infinity. So this time we have the lower limit of integration and the upper limit of integration both infinite. So I'm going to split the integral into two separate integrals. I'm going to first take the limit as b approaches negative infinity, so the lower limit then, from b to 0 of our integrand dx. And then I'm going to add the limit as b approaches positive infinity from 0 to b, because b is our upper limit, positive infinity. So basically I split those integrals at 0. Well, now I just need to take those antiderivatives. Antiderivative of 1 over 1 plus x squared is the inverse tangent of x. So this one is going to be evaluated from b to 0, because that's the limit as b approaches negative infinity, the lower limit. Then the rest of it is going to be the limit from 0 to b. So the right half of it, I guess you could call it. Fundamental theorem of calculus, part 2. Plug in 0, subtract plugging in b. The second part over here, I'm going to plug in b and then subtract plugging in 0. Now the inverse tangent of 0 is 0. The inverse tangent of b as b approaches negative infinity, well, I know that the inverse tangent curve looks something like this. So the limit as b approaches negative infinity is going to be negative pi over 2, but the limit as b approaches positive infinity is going to be positive pi over 2. The range of inverse tangent is negative pi over 2 to positive pi over 2. One piece of the tangent function flipped over y equals x, basically. Simplify a little bit more, and I get pi. Now try problem number 21, says evaluate the improper integral or state that it diverges. So again, we have an improper integral with both limits of integration being infinite. Now that's e to the negative absolute value of x dx. That's going to be interesting in just a second. It may be interesting now too, I don't know. So first we're going to split up the integral. So we're going to take the limit as b approaches negative infinity first from the antiderivative from b to 0 of our integrand dx. So b, the lower limit, is going to approach negative infinity, and we're splitting the integral at 0 just because it's easy. And then the limit as b approaches positive infinity then is going to be the antiderivative from 0 to b of e to the negative absolute value of x dx. Now, I know we've got some work to do here, but think about this. When we plug in positive infinity or negative infinity into our integrand, that absolute value is going to make it all positive no matter what. So we really have an even function here, which means I don't need to do both of these separately. I just have 2 of the limit as b approaches positive infinity from 0 to b of our integrand times dx. So now I can integrate that, which will be evaluated from 0 to b. Fundamental theorem part 2, plug in b and then subtract plugging in 0. Simplify. So now I have 2 times. Now as b approaches infinity, this e to the negative infinity will drop down to the denominator, so that becomes 0. But then e to the 0 is 1. And then that simplifies to be 2. So you can think of that as the area under the curve e to the negative absolute value of x from negative infinity to infinity is 2. Now because this is an even function, the area from 0 to infinity was 1, and the area from negative infinity to 0 was also 1.